solving the numerical, when solving the differential equation, ordinary differential equation numerically. The concept of stability is an important concept. Before you can see the book, page 353. The stability concept is an important issue in solving a numerical system, differential equation, because an unstable method may be leads us to untrue solution, the solution with a great error. So let me add. Salam alaikum. So when we use a certain type of method, a certain method for solving differential equation numerically, we should worry about the stable issue in this case, because an early error at the first step may become bigger and bigger in unstable condition. We need to show that with this system of equation, we have dy divided by dx, or y prime, as a function of x and y. As you can see here, minus 2y plus 2 with initial condition y at the 0 point equals minus 1. We want to show the issue of unstability or stability related to this problem using the multi-step simple formula. By solving this differential equation using analytical solutions from differential equation analytical solution, we can get the function yx as a 1 minus 2 exponential of minus 2x. The curve of this function is similar to the curve of exponential function, actually with some transformations or symmetry. So we know that the curve of these functions is smooth. Smooth means it's differentiable, or its derivatives are available for all orders. By starting at this point, initial point, for example, y0 equals minus 1, and going and continue with the solution of analytical solutions or exact solution, we can see that this it's a decreasing function, uh, 1 minus, it's an increasing function, and we want to experience that with this simple multi-step formula in MATLAB. Let me show that in MATLAB. Uh, at first, I open a new script in MATLAB. Let me, and we can define the step. For example, here we have h 4.1. We can then define the value of y, a variable to take the value of y at different points. You know, y index n plus 1. In order to define this in MATLAB, we use a certain kind of vector in MATLAB. For example, let me show you why. As a 1, as a 10 row and just 1 columns matrix or perpendicular vector as this. At the first, we let the value of y as 0. It became a 0 for all of its entries. Zeros, a command zeros in MATLAB refer to a matrix or vector with 0 elements in each of its elements, and we can define this formula, which shown as a 6.18 formula. Yn plus 1 equals yn minus 1 plus 2hf x1 by xn yn. This, let me define this formula in MATLAB. We need a for loop. Let me use and from 1 to, for example, 10, and yn plus 1, yn minus 1. You know, we have a equals y and minus 1 plus 2h f. Here 2 multiplied by h by a. Here, in order to show in MATLAB, I use F1. Just We name that as f1 x index n, and I need to define the vector of x, of course, and y, and let me define the value for x. You know, when we will start from the initial point y0 equals -1, the x, we start the values of x from 0, and by taking steps h, for example, o plus 1, o dot 1, o point 1, we can define the values of x. Let me x let me here x at the first we set the x as zeros and 1. Here we add these values x and equals x n minus 1 plus h. The values of x from 0 we change it h, and let me n equals n, and we use this as n, and we close this loop. Let me define the values of this function f minus 2y plus 2 in a separate function form. We have f1, and here we have an output, and here an x and y. We have two arguments, x and y. We define the values of x and y minus 2y plus 2. We save this in the same place as document MATLAB, and you can see here. Let me save that in the same place to know the functions. Let me run this stat for here we need to and we have errors. Um, Actually, we have some errors. Let me X. And zeros and 1. Let me test that. And actually, we have some problems here to solve to this. Let me assignment mismatch with such that it's zeros and zeros. So we need to y and plus 1. Let me here y2. We have some values for y, and you know, in order to get a real solution, y0 minus 1. Let me test that. Y0 minus 1. Let me show that y at the minus 1. We start from 1 minus 1, and we need two initial points when we use this method. We want to yn plus 1, yn minus 1, and that value. Let me we need to replace a value for y2. Let me find the values of y2. We have the analytical solution, 1 minus 2 exponential minus 2x. 1 minus 2, the exponential functions are minus 2, 2.1. Minus 63. What we can see here is that the results from this equation, which are shown in this table, for using this method, we need two values of yn plus 1, yn minus 1. You can see we here use a multi-step. For example, in the n plus 1 step, we use the informations of n minus 1 step, and 2h f. In f, we get the informations of the previous step, the end step. For example, we use two steps here to find to predict the information for the next step or n plus 1 steps. We can see the values for x, y, the exact analytical values, the error, and the related error here. Let's take a look at the errors here. We can see the amount of errors at the first step. The next step become less, and after that the amounts of error are going to increase and increase and increase. At point 4 we have 2.97 errors, which is a significant error, and our method no longer returns us exact or near exact solution. And the reason of that is because of we used an stable method, and let me show that. For example, when we use a simple Euler method, you can see simple Euler method was the first method we talked about, and it was not a very useful and very fast method, but For some kind, it gives us a stable algorithm that control the values of errors. For example, you can see the predicted value or the computed value of y, and the analytical or exact value, the amount of error here, the amount of error. At last, we have very few amount of errors. Our errors are very, very small, and you can see a type of a stable method despite some argument about the inefficiency of these methods, but it gives us a stable method. So what we need now is to be worried about stability of an algorithm or numerical approach. And we need to design or figure out something, a stable algorithm for solving a system of linear system, solving a differential equation. The book says observed in table 6.11. We have 6.11, this table. We have a good solution at the initial steps. For example, the amount of errors are very low. For example, until the 7th step, not 8 steps, 9 steps, and after that the amount of errors became significant and start to increase unboundedly, and at last we have such a very, very significant amount of errors. You see the difference between the computed and the exact or analytical solution of this differential equation or yx. We get a good results up to about x equals 4.8, but from x2 the computed values are increasingly poor, and as x approaches 4 they are completely useless. They're no longer beneficial for our differential equation. When we compare that with the results from simple Euler computation, also with the same steps, h equals 4.1, which shown in this table, 6.12, we can see at the first step the amounts of errors are low, and after that the amount of errors became to grow. But this is a kind of a stable algorithm, and we have controlled the amount of error. As you can see, the computed exact amount of error here. Compare this with the result from simple Euler computation, also with the same that are given. These are much less accurate and small values of x. On the other hand, the Euler results closely resemble the analytical values, close to analytical values, in other words, as the large values for x, and do not show some oscillations. We need to show something unstable in another method. this method of equation 6.8 is unstable while the Euler method is stable. The 6.18 formula was unstable because the errors grow significantly. There is another unstable method, but its instability is less apparent. Millen's method, we want to show that, is a multi-step predictor or predictor that uses this equation. We use two formula to compute the values of y at each steps. The first one, we predict the value of y based on this formula. F is also y prime equals f of the functions of x and y, and f refer to f index n refer to the function of f, the values of f at the point of n the steps for x and y at the steps n. The first one, we find the values for yn plus 1 and yn minus 3. And in second one, we use a new equation. For example, in the past, in previous example, we find the values for y, but here we find the values for yn plus 1 index c. C refers to character, and in that case we use the value of yn plus 1 to find the values of fn plus 1. In computing these values, for example, fn plus 1, we use the values of predictor yn plus 1 and xn plus 1. And this called the corrector. We can simply apply these algorithms in MATLAB or other languages, and let's solve the same equation in this previous example, but with the Millen's method. Y primes or dy dx equals fxy equals minus 2y plus 2 y0 equals minus 1 with the same initial conditions. And with the formula of Millen's method or formula of 6.19, we can see the oscillatory behavior or unstable behavior, which is shown in table 6.13. Can see here the exact value are shown in the third columns, which under the analytical x, y, analytical errors and related errors. We start from 4.4 because of our algorithm. We need 4 steps at the first, the values of, because in this case we use informations of previous steps, not just single previous step, but previous multiple steps. So we need the values of y at 0, 0.1, 0.2, and 0.3 to find the values of y at 0.4. You can see the amount of error in 4 columns of this table. This values for error are at the first at the initial steps are uh, very few and small numbers, and we can see until we reach the point 2. After that, we see some unstable behavior, and the values of error became to increase and increase. Uh, but until the point 8, they are not large, but they are increasing in magnitude. We want to further discuss the issue of stability in this case. Let me, at the first, let me show the values of y here. You can also find the analytical values. Let me analytical y y y refer to exact y exact y exact y. How can we compute that? We know the analytical solutions, 1 minus 1 minus 2 multiplied by exponential minus 2x multiplied by x at the step n. At the first, let me define the function for y exact equals zeros. First, the initial assignment for variables in MATLAB, m and 1. Let me zeros are exact and y exact at the end. Let me compute that in different loop, for example, for n equals 1, 11, for example. Have no errors at all. And 1.4. Dimensions of that is not equal as v 1 to 4 y2 y2. You can see the values. The first columns here, column in here is computed, and the second one is analytical, and we can see the difference. We can also show the difference between them. For example, here error y minus y exact. Here we can the amount of error at the initial steps. We have a very low amount of error, but as our steps are becoming bigger and bigger, the amount of our errors become significant. As you can see in this, you can simply apply these algorithms in computer. Let me talk about the issue of stability and instability. We have a differential equations, for example, y prime or dy dx equals ay, where a is a constant value. From analytical solution and from differential equations, we can easily find this value. The only functions that we know it's equals to its derivative is the exponential functions, and here we can simply notice that the solution is the C exponential functions of ax. And we want to discuss stability in this case. Suppose now that y at the initial point, yx0 equals y0 is the initial condition. It then follows that the values of c must be c equals, in differential equation, the value of c can be obtained from initial condition, for example, or boundary condition, partial differential equation. C equals y0 e minus ax0 by letting yn be the values of function when x equals xn. The analytical solution is as this: yn equals y0 a xn minus x 0 with this value of c. We want to solve the differential equations, but the methods of Milan we have from the corrected formula, this formula yn plus 1 equals yn minus 1 plus h divided by 3 y prime n plus 1 y prime is a y. This from the definition of the differentiation of y or derivatives of y. Plus 4y prime minus plus y prime at the n minus 1 step. This is a formula for multi-step formula. By letting y prime equals a yn y prime n from the original differential equation and rearranging the previous equation, we get this equation yn plus 1 equals yn minus 1 h divided by 3 a yn plus 1 for 8 yn a yn minus 1. This is the same as the previous one, and we can simply solve this equation for certain type of amount for a. Let me we can further rearrange this equation, for example, by taking the terms in the left or right side of this equation to the left side and arranging as these values, we get this equation, and which is the second order difference equation that has the solution yn equals c1 z1n plus c2 z2, and z1 and z2 are root of the quadratic equation. Let me take a look at this table. X by analytical errors, Milan's method. We can see based on our errors a certain amount of increasing of delay after the 0.8. By using some rearrangement with this one, the roots of the quadratic of this function of this equation is z1 and z2 based on the values of delta and the values of the methods of finding the roots of a quadratic equation. We get these values for y. What happens if the step size h became small as h tends to 0 and r going near to the 0 and r2 to the 0 even faster? We can neglect the 3 r2 term under these radicals in comparison to 1, and we get, after dividing the fractions, z1 is 2r plus 1 divided 1 minus r, and z2 as this fraction, and we can find the approximate values for z1 and z2. When we compared it with the Maclaurin or Taylor series for exponential functions, exponential of HA, the two term of that is 1 plus HA, and exponential of minus HA3 by two terms of is 1 minus HA3. You can know that exponential functions of H is let me exponential equals 1 plus x powered with n and factorial powered with 1 powered with 2 divided by 2 factorial. The exponential function, we have a series with this series, and based on this series we can get the exponential expansions of EHA, and the last one we can get the Z1 and Z2, and we can see the median solution is represented by these values. Yn equals C1 EHA, and from this one CH2 E minus HA3 powered with N, and vice versa. We can see in this we have used the difference between the first step and the last step as NH and multiplied by H, because we divided these intervals into the N subintervals with the length of H. The solution consists of two parts. The first term obviously agree with the analytical solution. The second term called parasitic term will die out as Xn increase if A is a positive constant. But if A is a negative, it will grow exponentially with this Xn. We can see the particular behavior or values for H. The small size is of no benefit in eliminating the errors because of unstable algorithm. When we use the small h, we need to find a better solution, but here is the opposite. And this is another issue we must take into consideration, and defining using a multi-step approach. In the previous example or previous method, like Millen's method, the instability comes from the character equation, but there are ways to avoid this instability. For example, using the Hamming's methods. Hamming methods is proposed a way of corrections that uh, avoid the instability. We use these equations. Y index I plus 1 P means refers to predictor equals Y I minus 3 plus 4H 2Fi minus Fi minus 1 and 2Fi minus 2. We simply notice or observe that this is a multi-step formula, and the predictor value of y index I plus 1p, which is first modified in the last one by Hamming's equations, by I plus 1m, m refer to modified predictor. After that, we modify that by these equations, yi plus 1, p, or which comes from the last equation, previous equation, minus and this fraction yip minus yicip refer to predictor, c refer to corrector at the previous steps, and the modified values is used in the corrector, which is the third equation in this screen. yi plus 1c is a corrector, and it's equals to these values, 1 divided by 8 from this value, and the errors of this method is not as small as with the millions, but it is little better than Adam's molten ones. Uh, Here I'm going to uh, show this with the we can simply use this in MATLAB, just a three equation we can use in a single loop function, but before we show this, I want to uh, let you 10 minutes rest. After that, we use the Hamming methods in MATLAB, and we show that how we can apply or deploy these algorithms on MATLAB software very easily. And 10 minutes rest. After that, we continue this. Any question before the rest, I'm ready to answer to you. Any questions? So no questions. You have a 10-minute rest. I will start that after 10 minutes until the next 10 minutes. Bye bye. Yeah. We delivered that for the next meeting because that's higher order equations and systems is important. Hamming method in MATLAB, we show that in the next meeting. You know, in nature, in practice, we have different phenomena, and by using a mathematical model for this phenomena in some kind, we obtain differential equations of higher order, for example, of second order, third order, and other order as well. For example, when we know the Newton's law of motion, for example, F equals m, the mass of an object with the a is accelerations, and we know that the acceleration is the second order derivatives of x with respect to the time xt. F equals m day 2x divided by day t2. This is the second order differential equation. F equals m multiplied by a differential values. How we can solve this system of equations numerically? There are different ways, and in this case, we want to show different methods of solving the differential equations in higher order. Here we can find the second order derivatives of x with respect to t as a f, the fraction of m by n. Actually, we can transform a higher order differential equation to the system of single order differential equation. For example, by letting dx divided by dt as a y, a new variable as a y, we have this system of equation, dx dt or x prime t equals y, and dfy divided by dt, this fraction as f divided by m. In reality, dy divided by dt is actually the dx divided by dt2, or the second derivative of x with respect to t. This system of single order differential equation is much more easy to solve numerically. To solve the original second order equation for x as a function of time, we need two initial conditions: the starting position x0 and the starting velocity. Velocity is the first order derivatives of x with respect to time. So the equations of dx dt begins with x equals x0 and dy dt equals with y equals y0 or x prime 0. Let me show another example. We have a system of mass, wheel and a spring in this figure 6.3, and in order to model or formulate this mathematically, we use a higher order differential equation for example, for acceleration, for force, or, in system of spring, the force equals mass by accelerations equals k as a parameters of the spring, with x as the positions of the mass. And finally, the equation of motions of this system. This system has a certain type of motions, maybe fluctuations or oscillations of this mass. And this motion is described by these two differential equations. The first one for the first mass and the second one for the medium mass or M1. And we want to solve this system of equation, differential equation, to analyze the motions of this combined system of springs and mass. And we want to talk about the solutions of this differential equation in numerical form. We can transform this system of differential equation to a higher order differential equation to a new system of single order differential equation or first order differential equation by substituting the dy divided by dt instead of the second order derivations of x1 with respect to t, and the dz divided by dt or z prime for the second order differential derivatives of x2 with respect to time. The x1 is the positions of the first mass, and the x2 is position of the second mass. And finally, this system of equations is transformed to a system of four differential equations with the single order differentials by adding two variables, z and y, and its derivatives. So now we focus and concentrate our attention to the system of single order differential equation instead of higher order differential equation, because this is much simpler and we can transform the higher order differential equation to a system of differential equation. It is clear that all we need to do to solve higher order equations, even a system of higher order initial value problems, is to reduce them to a system of reduced differential order, system of first order equations. And here we illustrate how a system of the first order problems can be solved with a pair of equations. Uh, with these initial values and taking a certain step, we have this system of differential equations, first order differential equation in this box, which shown as a 6.20. dx dt xy plus b and dy dt dy plus x, x0 equals 1 and y0 equals minus 1. The first approach to solve this system of equation in a numerical fashion is to use a Taylor series method or Taylor expansion. Let's take a look at this equation in this box, 6.20. dx the dt is the x prime, dy the dt y prime, and we want to take a various derivatives x prime, x double prime, and x triple prime, and vice versa, and the same for y prime, y double prime, and y triple prime. And this value should be evaluated at the initial point of time. We have x prime equals xy plus t, so x prime at the 0. We can find that from these initial points. X as the point 0, initial x, initial y, and t. 1 minus 1 plus 0 is minus 1. Y prime, we can find the initial value of y. Y prime as 1. By taking derivatives of x prime, we can easily find the second derivatives of x with respect to t by taking derivatives of x prime. xy, derivatives of xy prime plus x prime y. The first the two terms multiplied by each other, the derivatives is the derivatives of the first term multiplied by second, and the derivatives of the second multiplied by first, plus the derivatives of t with respect to t. Here we take derivation with respect to variable, independent variable t, and x and y are the dependent variable in this case. The values of the second order differential equations of x we can find from the previous values x prime and y prime, as you can see here. In this line I have emphasized on x, y prime at the initial point, the values of x is 1, y is minus 1, x prime is minus 1, y prime is 1, and we can find that x double prime as 3. In similar approach, we can get the second derivatives of y from the first derivatives of y. Ty plus x, the derivative means y plus ty prime plus x prime, and by double prime at this initial point of time 0 equals y, which is -1, t by prime equals to 0 at the end, minus plus x prime is -1 from previous formula. This algorithm is kind of recursive algorithm to solve a system of linear equation. X triple prime, y triple prime are simply computed, and the values at the initial point is -7 and 5. And we have these values of derivatives at initial point at the 0. When we use the Taylor expansions of x as functions of independent variable t, x equals the values of x at the 0 plus the values of its derivatives, the first order derivatives at the 0, multiplied by t, and the values of plus the values of the second derivatives of x, which is 3, divided by 2 factorial. As you can see, 3 to this fraction multiplied by t2, and simply this methods continues for evaluating the x. As you can see, we can find the value of y as a simple manner. Y0 is -1, y prime 0 is 1, y double prime 0 is -2, divided by 2 factorial is -1, t2, and on, and we continue this. We found the Taylor expansions of the Fy. It's quite useful. When we have a Taylor's expansion of a function, we have a very suitable expansions of these function, suitable approximations of this function as well. And by taking a t as 0.1, we can compute the value of x from this formula, and the value of y at this point from this formula, and x is 0.9139, and y is -0.091992. This is a Taylor series approach for solve the system of single order differential equation. If you have any questions in this case, any question? If you have any questions or any uncertainty, you can ask me or leave your comments in our WhatsApp group or in this Google meeting, or in our Vadana. Our Vadana is open for me, but you are not in our Vadana system. Equation 6.21. This equation, this system of equation, are the solution to the set of 6.20 in this box. system of differential equations, and we should find another ways in getting derivatives. For example, we cannot get x double prime 0 until y prime 0 is now. We cannot get y triple prime 0 until x triple x double prime 0 is known. After we have obtained the coefficients of Taylor series expansion in this system of equation, we can evaluate an x and y as a functions of independent variable t, and the error are really depends on how many terms we can compute. For example, here we compute the sixth term of each term, and it's really depends on how exact our solution is and how error is acceptable to us, how much amount of error is acceptable to us. As we can see, the Taylor expansion method is very simple but useful, and a single step approach to find a solution. Why a single system approach? Because we find the solution based on the values of x at the initial points or the previous steps. We can use a multiple step approach or a kind of predictor corrector method, which is here you can see the modified Euler approach. We can apply in the next approach or predictor corrector method. We can apply the predictor to each equation, then the corrector can be used again. Note that we work alternately with two functions, yp and xp. Take h as 0.1 or step as 0.1. P and C indicate the predicted and corrected value in these computations, as well as previous indexes of P and C, which both refer to predicted and corrected. The predicted value of x at the next step or 4.1 equals 1 plus, we use this equation, this system of equation. The value of x. xy plus t. X at the initial point, x0 is 1, y0 is minus 1. X at the next step equals x at the initial point plus h fxy or x prime t xy plus t. Here x1 y minus 1 plus t equals t at the last previous step 0.9. The predictor value of y equals the initial value of y plus a step, and the y prime formula, which is the y py plus x is 0, y minus 1, x is 1, and the value is minus 0.9. And then we use the correct the values of x and y in the corrector formula, which is the x at the initial point, 4.1 is h, and 0.9 is the predicted value of x, y, and 0.1 is the values of t, as you can see here, the initial value of x, y, divided by 2 as a formula for corrector, and the corrector values of x you can see here. Also, the corrected value plus 0.1, which is the first value of x and y at the initial point. 0.1 is h, 1 is the values of x, and you can see x plus ty plus t or h minus 9, the predicted value of y, p plus the corrected value of x, as you can see here, divided by 2, and the corrected value of y is obtained as minus 0.9, and we can notice the difference between predicted and the corrected value. Here, in computing the corrected value of x at first step, we use the predicted value of x and y. In computing the corrected value of y, also the corrected value of x is known, and we have a choice between the corrected value of the predicted value of x or the corrected value of x corrected. The best choice is using the corrected value of x, because it gives us a much more accurate solution. This is an intuitive field that one should use the corrected value of x or xc with the idea that one should always use the best available values. This does not always expedite or fasten convergence due to compensating errors. Here we have used the best values to date. If we use the corrected value to compute the value of derivatives at h, we can obtain better values, which is x and y. And for using as h 0.1. We can use the same approach for the next steps with this same step. And the error is also, we have two kind of error. The first one is the truncation error because we cut the additional term in these two Taylor expansion and here as well. So we want to use more advanced approach in solving the system of single order differential equation instead of higher order differential equation. The next approach is a Runge-Kutta-Fehlberg method in the case of system of linear equation instead of single equation. Again, there is an alternation. We have different options here, how to calculate x and y in each option. But we want to use the informations of previous k steps, not just the previous single or two steps. Previous k steps, which is maybe or probability or probably a more suitable solution and gives us more accurate solution because we use the informations of last multiple steps. We have this system of equation as we studied that in the previous approach. We have the same equation, differential equation, and we want to solve this with the Runge-Kutta-Fehlberg method. In Fehlberg methods, as a single differential equation, we have to evaluate the values of k's, for example, for x and y for both of them. Here we use the notation k index 1x, which k1 referred to x, the first k, and referred to x, and k1 y, the first y referred to y. H, f. H is our steps, and f related to this function. And for k1 y, we use the hg. H is the steps, and g is this function. And we compute the k1x and y both for x and y, and we can see the values for k's is minus 0.1 and 0.1 for x and y respectively. We can compute the k2x and k2y based on the values of hf. We have hf, f is actually this one, and j is the values of k2, k3s for both, and x1 is computed as well, k6, k6y. And the final step of finding the values of x and y at the next step after computing the k's values is here. X 0.1 is computed. Y 0.1 is computed as well. This is the fifth order Runge-Kutta-Helberg method, uh, which is applied or deployed for a system of differential equations. Extending the Taylor series solution even further shows that the Runge-Kutta-Helberg values are correct to more than 5 decimals or 5 digits after the decimal. Here's the modified Euler values are correct to only 3 as with the same step for h equals 0.1 for both approach. We use this approach, we can compute the values of x and y and in another points, for example, x 0.2, 0.3, 0.4, and of course the amount of errors became less than the amount of error in Euler or modified Euler predictor corrector approach. Here we have the values of system of predictor corrected method. You can see the value of x and y. The final value of y and the final value of x, when we compare that to the final value of x and y with the Runge-Kutta approach, and we can see the difference between them as the errors. Other approaches we have studied in the previous meetings, for example, for single differential equations, can be applied to multiple or system of different single differential equations, which is the next. You can see we can apply the Adams-Moulton method in this case as well. After getting 4 starting values, for example, 0.1, 0.2, 0.3, and 0.4, we can proceed with the algorithms of Adams-Moulton methods. And compute the values of x and y. Let me go back to Adams-Moulton methods. Six point 16 and 6.17. Adams-Moulton method. This is the Adams-Moulton methods. We can use this for evaluating the values of each of these variables, x, y, or maybe another variables, for example, z and w, maybe the predictor, the corrector, and the solution x as the next step can be computed with the equation 6.16, 6.17, and the values of x is computed at this value. The value of y can be computed at this value, and by evaluating or getting the values of the derivatives of x and y at this step, by using these two computed values, we can correct these two values in the correction formula as well, and the values of x is corrected to these values 0.91, 39, 36, and the values of y is corrected to this value, which is, you can see, is the same as the predicted value for y. And also this has a meaning for us. Both the predicted and the corrected value are the same, which shows the accuracy until the 6 decimals or 6 decimals of accuracy. We can compute and continue this approach to find the solution for larger values of t, for example 0.2, 0.3, 1, 2, 3, and further values of t, and the solution work as well. Yes, we have the book have some commands you can use in the Maple if you are familiar with the Maple approach. But actually, you can solve all of these equations with MATLAB, for example. MATLAB is much more easier than Maple, and is used much more than Maple in practical. And as you have seen in these MATLAB programs that I can solve in this course, as the time agree with the solving, it's very easy to code a computer and use these algorithms to solve a system of a system of differential equations, and we can use these equations, this algorithm to solve in MATLAB, for example, or Python. Let me at the first, if you have any question or uncertainty about using these values, these equations, You can ask me or leave your comments. Uh, Let me highlight this point that all of these algorithms, for example, multi-steps, Adams, Moulton, and Range-Kuta, these computations are time-consuming, and we cannot do this by hand. This is kind of algorithms that we are going to use in uh, computer code, and the computer can compute these values very easily, and I recommend you to solve these values by the computer and start solving this with the computer code. Today I want to finish this course and this meeting.